So Emre will talk about exponential separations using guarded extension variables. Go ahead.
Hello and welcome. So since this is also my speaking skills talk, it will be rather general, which is fine to do because I assume that none of you are familiar with the proof systems that I'm gonna try to separate in the talk anyway. So the majority of the talk will actually be just background, me telling you about these systems, giving their definitions, providing examples. And at the very end, I'll show you the results and tell you a little bit about how the proofs are done if I have some time, right? So this is a talk in proof complexity. So let me give you some brief intro to proof systems. So we are working in propositional logic. We have propositional formulas, let's say they're canonically in CNF form. An abstract proof system is a verifier of proofs, polynomial time verifier of proofs. And more formally, you need two conditions aside from this polynomial time verifiability. For every claimed proof, if you can make your verifier accept the proof for a formula, then that formula better be unsatisfiable. Otherwise, you're doing something unsound. And if your formula is satisfiable, then completeness says there needs to be some proof to make the verifier accept. Okay, so these are quite natural expected properties that you want from a proof system. Yes, these are, so proof and refutation, I mean the same thing throughout this talk. And this is quite abstract, and this was defined this way originally to make connections to the broader computational complexity. But in reality, people generally study concrete proof systems which have like axioms, inference rules, certificates. And this is like a list of proof systems just to show something that I'm sure that everybody has at least heard something in this list of. So truth tables are the least interesting proof system, but they are a proof system according to this definition. In this talk, I will focus on resolution, so sequent, calculus, Frege, and this line is mostly logical proof systems. These are like algebraic ones. These are called semi-algebraic proof systems. This is the so-called geometric proof system. Those are mostly of interest in algorithm design. These have connections somewhat to like closer connections to the broader study of computational complexity. And so in proof complexity, we are interested in this quantity. Yes?
Can you explain the unsatisfiability condition again?
Yes, so you have a formula. If there is no assignment to the variables in the formula that makes it satisfiable, then that formula is unsatisfiable.
Okay, so how does that match the definition?
Well, in the definition, so this is like a for all formulas kind of thing. Okay, so throughout this definition, like this is kind of informal. This is like for all formulas, for every claim proof, if this holds, then that formula is unsatisfiable. And for all formulas, if that formula is unsatisfiable, then there exists some proof of it. Good?
Do you want understanding what the proof system, like what the P is actually?
Oh, P is just some polynomial time relation, which you may think of as like being implemented by some Turing machine. That doesn't matter that.
Okay, so it's like, it could be an assignment of variables to values or something?
No, that we are satisfying we're certifying.
Can everyone hear on Zoom now? Yeah, sorry to interrupt.
Yes. When you say polynomial time, you mean in the size of just gamma or gamma and
In the kind of thing.
so pi, including pi?
Yes.
So if you have a really large proof object,
Yes.
you can get very efficient verifiers.
Yes.
requiring it to be efficient in the size of this forces the condition upon the size of the proof, which is quite non-trivial, and I will say a little bit more about it. Okay, so all clear? So we're interested in this quantity, and I'm leaving it purposefully vague. So it's this function is the size of the smallest proof of this gamma in your chosen proof system P. Size generally is proof system dependent, although people often choose the size such that it corresponds to the measure that everybody eventually cares about in complexity, which is like the bits, number of bits required to write down the proof. And in proof complexity, we are interested in that function as a function of the size of the formula. The size of the formula is often the number of symbols in the formula. Again, I'm leaving it a little bit vague because actually it should be the number of bits required to write the formula down. But the size of the number of the symbols appearing in the formula kind of stands in for that it's close enough. So we, in proof complexity, compare proof systems by relating them to each other in the manner that you do with complexity classes. So suppose you have two proof systems. One relation that between them that can hold is simulation. So you say that a proof system simulates another system if its proofs for all formulas are not that much larger than proofs in another system of the same formula. Okay. In other words, you can think of this as there is an algorithm such that if I give you a Q proof of a formula gamma, then that algorithm gives you a P proof of gamma, such that the proof is not that much bigger than the Q proof. Okay. If you can do this for all formulas, then you say P simulates P. Okay. So Q proofs can be efficiently converted to P proofs. And you also separate formulas. You could have multiple definitions for separation. This is the one that I chose for this talk. So you say P is separated from Q. If there is some sequence such that it has short proofs in P, but it requires long proofs in Q. Okay. Okay. And you say two systems are equivalent if they each simulate each other. And you say two systems are incomparable if they are both separated from one another. Okay. And if a system both simulates and is separated from another, you say it's stronger, strictly stronger. Okay. And so proof complexity asks really wide-reaching questions like, is there a polynomially bound proof system? Namely, is there a system which has short proofs of all the formulas, all the unsatisfiable formulas? And this is connected to problems about complexity classes. It asks, is there an optimal proof system? Namely, one that simulates every other proof system? Or can we actually search for proofs that are of similar size to the minimum size of the certain system? Let's say I give you some system and I ask you, can you give me a proof of this formula that is as small as possible? If you can do this while staying as close to the minimum size of the minimum proof size in that proof system, then you can efficiently find near minimum size proofs. But those are, again, like questions mostly about the abstract proof system. And more commonly, people study concrete proof systems.
Sorry, but polynomially bounded in what quantity?
Polynomially bounded in the relationship of this minimum proof size with respect to the formula size. So this is the question about the question that you asked earlier. Like if everything has a short proof in its size in a particular proof system, that proof system is polynomially bound. Okay. All right. And this talk, we are focusing on this concrete, really simple proof system. So this refutes formulas in conjunctive normal form, which we will view as sets of clauses. I assume familiarity with like what I mean by clause, literal, variable, negation, and all that. So clause is a disjunction of literal, and literal is a negated or non-negated variable, propositional variable. And so in resolution, you have a single rule. And this rule says, in my set, if I have a clause matching this pattern, which is A is a clause, X is a variable, and B is a clause, not X is a variable. Again, X is a variable, so not X is a literal. Then you can derive this clause. Okay, this is like the cut rule or the modus ponens rule, which you're familiar with in your daily reasoning. This is like a restricted form of it, where you say this X has to be a variable. This is a sound and complete proof system. I will not get into either of those. But this is like the most widely studied proof system, improved complexity, because it's like the simplest system that is still non-trivial. Like the questions about it are not really easy to answer, which also has some practical significance, which I will also get into later. Okay, so here is like an example of a proof. So this is my formula, and here I switched to writing negations with overlines, just to, for readability. So this is your formula, and I'm claiming it's unsatisfiable. And you want to give me your proof of it in resolution, let's say. So like Catherine asked, you could just say, well, here, so there are 3 variables here. Here are the list of 8 assignments. Look, none of them are satisfying the formula, so this formula is unsatisfiable. That constitutes a proof as well. Well, in resolution, you do it a little differently. Formally, the proof is a sequence of clauses. So you first start by listing the clauses of the formula. This is mostly an aesthetic preference, but everybody does it that way. And then you start your proof. And in the proof, each item in the sequence is a clause that could be derived from some two previous clauses occurring in the sequence by applying the resolution. Okay, you don't really say in this form, at least. Don't mind this one right now. In this form, you don't really say how you derive it. You leave it to the verifier to say, oh, I see like there are some clauses here that could be resolved to give you this. And then you want to derive this one, and this one follows from the clauses here, and so on, until you derive the empty clause. Okay. And since this system is sound, if you derive empty clause, which is by definition unsatisfiable, you certify that the formula is unsatisfiable. And I could also arrange this proof in tree form by like showing which inferences I'm making very explicitly. Like for instance, this V, I will tell you here how it was derived. Here I'm saying, okay, it's derived from these 2 clauses in the original formula. And finally, like you have the empty clause. So these are like corresponding to the same proof. There is one difference though. In this proof, you derive Z twice using the same derivation. So this is also common in proof complexity to parameterize the proof systems with respect to some measures in various ways. So for instance, here you could say, well, I'm counting the size of the proof as the number of nodes appearing in this tree, which means that you have to pay for this twice, here and here. Or you could say, I'm just looking at the sequence and the things that appear there. I'm not deriving Z twice there because it's already in the list of clauses that I've already derived. So, I can reuse it. So in this case, you get something like called general resolution and tree-like resolution, and you can study their proof complexity separately, and they have different properties. And the practical reason that resolution is widely studied is because it's connected to SAT solving. So when I say SAT solving, I mean the practice of SAT solving, where you implement things and run them. So it's kind of separate from the theoretical study of decision algorithms for SAT. So the practical solvers are generally based on backtracking search. You pick some variables, you try to assign them to things, you reach a conflict, you backtrack, and you do the same until you reach nothing but conflict. Okay? And in practice, when a solver says this formula is unsatisfiable, like you run your program and it says unsatisfiable, you don't just trust it because it may have bugs in it, maybe something may have gone wrong. As the algorithm was running, you expect it to give you a proof. And for the main paradigms in this practical SAT solving, there's a real close connection to the proof systems, to concrete proof systems, in particular resolution. So this DPLL, doesn't matter what it is, again, I just put the acronyms here, but DPLL was common in 1960s, and it corresponds really closely to tree-like resolution. And the CDCL came up in the 90s, and it corresponds really closely to general resolution. And by corresponds, I mean there's a relationship in 2 directions. So this is like a complicated algorithm. If I give you some trace of a run of this algorithm, then you can extract from that run a resolution proof, a general resolution proof that is of comparable size to the time that the run took. And conversely, if I give you a general resolution proof, you can convert that into a CDCL run, an artificial CDCL run, that would take comparable time to the size of the proof. So in this sense, CDCL is like non-deterministically equivalent to general resolution, because when doing the converse,
I have to assume that I have perfect heuristics. I made all the choices in the algorithm in the most optimal way, and I got the shortest route. And then in practice, often you hear people say, well, set solvers are running fast, but there are all those lower bounds on resolution, and set solvers are based on CDCL. Why are they running fast despite this hardness? There's not a perfect explanation, but I'm saying one reason that should obviously not be true is because in reality, the actual set solvers, the real implementations, do not just limit themselves to CDCL. They do a bunch of pre-processing to the formula. They add clauses, they remove clauses, they rewrite the formula as the search is going on. And they tap into a little bit of the power of the system extend resolution, which I haven't defined yet, but it's like a super strong version of general resolution that simulates all the systems that I showed in the first slide. Okay, so there's like a partial explanation more for why the set solvers are doing that. And there are some caveats around this. So when logging CDCL, you use general resolution, but actually you use another system. Again, the acronyms do not matter. I'm just showing them. You use some system that generalizes resolution, but is also like equivalent to it in the sense that resolution also simulates this, but with some overhead. And the same goes for extend resolution. For running an actual set solver and logging its actions, you don't use extend resolution, but you use some system that generalizes extend resolution. And extend resolution also simulates the system, but with some overhead. And in practice, you don't like those overheads. So in practice, people use those. For instance, if you've heard of like Maran's 200 terabyte proofs, those are in this DRAC proof system. And extend resolution would simulate DRAC with something like n to the 4 overhead. So if you were hitting the worst case with that proof, you would require 200 to the 4 terabytes for your proof, which is a no-go. So people in general use DRAC. And this will be the starting point for the systems in this talk. So this extend resolution, the gist of what it does is it's able to make definitions. It's able to define new variables the way you're doing when you're writing your proof in formula. Let's say you may just create a new variable and say, well, let X stand for something, something. And then in the rest of your proof, you might keep reusing that X. Okay. And you can imagine how this leads to decreases in the size of the proof, because it stands for some large thing, let's say, which you keep reusing. So you're not incurring the cost of rewriting the thing that it stands for every time you use the variable. So this ability to make definitions is dangerous in the sense that it gives you a lot of power and makes the systems a little hard to analyze. And in this talk, we will focus on the variants of this DRAC that do not have this ability. Okay, but they will still be, they will not collapse to resolution. They will still be interesting systems that are between resolution and extended resolution in strength. Okay, and that's because they are able to carry out a type of reasoning which is quite common in your informal mathematical writing, which almost none of the systems that I showed in the first slide are naturally able to carry out, which is the use of this phrase, which I'm sure all of you have actually written in your paper somewhere or read it somewhere a lot of times in your life. And you may use this by writing this, for instance. You say, without loss of generality, you're proving something about two real numbers, X and Y. You say, well, there are two cases, either X is greater than Y or Y is greater than X. Let me just assume I'm in the first case. I will write my proof. The proof of the second case, I'm just leaving it to the reader because it'll just swap the variables in my proof and everything remains valid. So you can carry out that kind of reasoning. And this leads to a simplification or shortening of the proofs. So it's quite natural to study in proof complexity. Anything that shortens proofs, we like. So you could also say, for instance, you're talking about the graph and let's say the coloring of the graph, and you just pick some vertex and say, well, assume without loss of generality that this is red. And then you carry out the rest of your reasoning. Again, you can justify this in a similar manner. You could say, if it wasn't red, I could swap the colors. Like if it was blue, I could swap blue and red in the rest of my proof and everything is still fine. Or you could say, I'm sure you've written this, you could say, assume that the random variable has expected value 0, like somewhere. And then you prove some theorem about that random variable, and then you extract a more general theorem about some random variable by like translating the random variable. And there are plenty of examples of this. This is like really pervasive in daily mathematical reasoning. And so, okay, we're focusing in this talk on systems that capture reasoning without loss of generality at the level of propositional logic. Like I said, so extended resolution is quite strong. It can already capture this kind of reasoning, but it's a little bit overkill. It captures much more than that. We want like systems that just that have the just right amount of strength while still being able to capture this kind of reasoning. And now I'm moving into the formal parts of the talk, so I will show some definitions. And the way we formalize this, like what does it mean? So here, because this is usually used informally, like what's going on logically when you make that assumption exactly? So you're basically attaching clauses to your formula that are redundant. So redundant means adding it to your formula doesn't change its satisfiable state. So this is true of implied clauses as well. So if you take any normal proof system and keep deriving some clauses from your formula, then anything you add, it doesn't change the satisfiable status of your formula because it's implied. But this is a weaker notion than implication, in that it doesn't require, so for a clause to be redundant, it doesn't have to be implied. It's also, keep in mind for the rest of the talk, that it's a semantic property. So you cannot necessarily check efficiently whether this holds. And we are trying to define proof systems that will allow you to add redundant clauses. So if we want to satisfy that polynomial time verifiability condition, we will work with restrictions of this relation, this implication relation, that you can check efficiently, so that we get proper proof systems. Otherwise, we get something that's too strong and you can just prove a formula in a single step. Like if we could verify this implication relationship in a single shot, you could say empty clause. It's equally satisfiable, like if I add it to the formula, and you would have a proof. But we don't want that because we want to be able to check the proofs efficiently. And these rules will be obtained as restrictions of this. And before we move on to those restrictions, I will show you one small characterization of satisfiability, which gives us like a systematic way of obtaining various parameterized restrictions of this relationship, which will give us an entire zoo of proof systems, which we will then compare with one another.
Can I ask you a quick question?
Yes.
This is some semantic implication?
Yes.
So can you give a quick example of where C is redundant, but you don't have this?
I have that example in two slides. So first, so here's this lemma that characterizes equally satisfiable, like redundancy in terms of implication, which we understand a little bit better. This is my notation for saying this is a partial assignment to the variables, restrict this formula under this assignment. Think of this as you take this formula, I give you some assignment, you plug the values in the formula for the variables, and then you simplify the formula. Like if you have, for instance, in your CNF, you have a clause that includes the variable that's assigned to 1 by its assignment, then you remove that clause because it's an or of variables, one of which is satisfied, that clause is satisfied, so you can just take it out of the equation. Or if a variable is falsified in the clause, you just delete that variable from your clause. Okay. And so we characterize redundancy in this manner. And I don't want you to try to parse this really hard. I will just appeal to your intuition about the usual math reasoning again. So this is saying, I have my set of hypotheses at hand, and I want to assume, let's say the C corresponds to some case of the proof that you want to assume you're in. This thing, if I was not in this case, okay, suppose this didn't hold, then I could first make a change to my current case, such that the result is the same as having been in this case. Okay, this is quite informal because I don't want to get into all the definitions of the terms here. I will explain it with an example right now. So this is a very trivial example of a redundant clause that is not implied. So you have this formula of a single clause, X or Y, and you want to say, well, you haven't told me anything else about X and Y, so I might as well just assume that this junction is satisfied by setting X to Y instead of Y. Okay, so this is clearly not implied. You can just see by inspection, if you set X to 0 and Y to 1, well, no one is satisfied that this junction is satisfied, but this C is false. So you're not necessarily in this case. And the way you justify the redundancy of this is by using that lemma, which also corresponds to this informal reasoning, where you say, well, if I was in any other case, I could just set X to 1 instead. And I'm back in the case that I want. but you need to justify that you haven't lost any generality there, and that's where that lemma comes in. So here, for instance, you say, well, if I was in this case, like if I had an assignment to the variables that satisfied this, which would mean, this is satisfied and this is satisfied. And since this is the negation of the case that I'm in this case, x would have to be 0. You're saying, well, before that assignment, I could apply something, like I could override part of that assignment such that this thing is now satisfied by the overridden assignment. Okay, so you're basically saying, if I was in the case where x is not true, then I could just turn it true, and it doesn't hurt anything. And here you need to check that this implication holds, of course. But again, that's not in general doable efficiently, which is why we resort to like syntactic restrictions of this relationship. Namely, I will give you some conditions that a clause has to satisfy, which you can just check syntactically, such that if they hold, then the clause is redundant. Okay, this will not be a necessary condition for redundancy, but this will be a sufficient condition for redundancy. And since it will be efficiently checkable, we will be able to use it to define proof systems. Okay, so this is the only definition that I actually want you to remember that's kind of complicated. This is the notion of a block clause, which is a criterion for redundant clause. So a clause of the shape, which has a distinguished literal P, and the rest of it, C prime, where P doesn't appear, is blocked for P. We indicate which clause and which literal is blocked, but for P, with respect to the formula, if something holds for all the clauses in the formula. Namely, for all the clauses that contain not P, the resolvent of the two clauses, which is C prime, D prime, is tautological. And tautological here means, in the context of clauses, it has some literal that has appears as both positively and negatively in the result. Okay, so suppose like C was something like PQ, and then D was not P, not Q. Okay, the resolvent is Q or not Q, so it is tautological. So for instance, that clause would be redundant with respect to that formula. And here's like a bigger example.
This is syntactically tautological, right?
It
just becomes one after syntactic simplification.
Yes, so I mean, tautological here just stands for something that's implied by gamma. You could just pick, instead of tautological, you could replace this by any condition such that that resulting clause is implied by gamma.
Okay, but you've just chosen.
I've just chosen tautological. Yes, this is like the most trivial thing you could do. So this is the simplest notion of redundancy. And this is an example. So this clause is blocked with respect to this formula for X and Y and not Z. And also note that it doesn't have to be blocked for all literals or anything. You just need to exhibit one literal in the formula such that this condition holds. So X is one such literal, for instance. You could just check against all the clauses in the formula. You could resolve those and you get this syntactic tautologicalness because Y and not Y are there. And against this, you do the check and not Z and Z are there. And against this, there's nothing to check. So in particular, this means that, for instance, if P was a new variable, if P was a variable not occurring in gamma, then something that clause would be just vacuously tautological. Okay? And this is not formal, but in that way, these systems actually generalize extended resolution because you can simulate what extended resolution is doing by introducing new variables by just saying, oh, I'm picking this P to be a new variable that doesn't occur in the formula, and I'm able to derive the same clause as that really strong system. That's why we will focus on clauses like this, which do not have any new variable. Okay, and it's also blocked for Y. You do the same check. It's not blocked for not Z, though. So this clause passes the check. There's nothing to check here, but this clause doesn't pass the check because the result is X or Y, which is not tautological. Okay.
I can think of it as like this clause is blocked. This formula, like you can tell, at least currently, it's pointless to use the resolution rule with this clause.
Yes. I mean, at least over P. You would
that's what I mean, like with
yes.
P, yeah.
You could resolve this over other variables and get something interesting.
And like perhaps later it'll become unblocked, or is it like blocked forever?
It is blocked forever because this is like a universally quantified statement, right? So unless you somehow lose clauses, this is forever blocked. As long as you just keep adding clauses to the formula.
You might imagine you're like going along a resolution and you look at this clause and you're like, I can tell in advance I will never resolve this clause with variable p. Let me just make a note to myself.
And then you edit.
Then you add it.
Like why do you want to make that note?
Oh, should we imagine that this block clause already appears in our proof? Or that it hasn't?
No, I will define an inference rule that allows you to add such clauses.
I see, okay.
So this clause is redundant. It's not implied necessarily. And I will take this and resolution. Resolution is already complete. I'll just add this as a rule to resolution with the hope that it somehow shortens the proofs.
Okay.
Okay. And I will skip, I was going to show its redundancy, but I will skip it. Like that, you can justify using the lemma that I showed earlier that it is redundant, but yeah, to get into that. And then, so this is like the most bare bones notion of syntactic redundancy that you can imagine. There are ways to generalize this, and those also give rise to different proof systems. And so we are interested in saying, you know, if I have different notions of redundancy, do I get different strength in my proof systems? This is like kind of saying, when making a justification for saying something is without loss of generality, you limit the strength of the justification that you can make. If you are able to, you know, not very limited, and if you're able to make really strong justifications, then you should get something stronger. And that gives rise to proof systems of different power. And I will just flash this, but again, don't parse this. This part is literally the same. This is also the same. You just relax it further by saying subsume. Subsumed means this clause is, so there is some clause in this formula that is a subset of this clause. This is also implied. This is just a more relaxed condition than just saying tautological. Okay, and this gives rise to another proof system. The name of this, which doesn't matter, it will be right. And you could generalize this in other directions as well. So why just look at a single literal P? Again, do not parse this, but just stare at like this part, and this part. So instead of this P, you could pick out a bunch of literals in the formula. And you could define an analogous rule that says, okay, this is tautological. Or you could even mix and match with the previous definition. You could say this is tautological or subsumed. Okay, in this case, where you have like orthogonal changes that you can make to these rules that give you different proof systems, which lead to like different parameterizations of this without loss of generality reasoning. Okay, yes.
Just to clarify, so normally in a proof system, redundancy might be a bad thing because why would you do redundant work, right? But here it's a good thing because it allows you to make your proofs shorter.
Yes, so redundant maybe is not a great name for it, but it basically says that the satisfiability of this formula isn't affected whether you add, like it's redundant for its satisfiable states. You could remove them. I didn't tell you that, but you could also remove them or add them. Okay. And for instance, fast followers in reality do things like, okay, this is redundant, but I will add this one because it will lead to a shorter proof later on. Like for extended resolution, for instance, what it does is also redundant. You don't have to define a new variable to stand in for something. You could just inline all your definitions in the proof. So think of it like you're using some lemma in your proof. You don't have to like isolate that lemma to something and then say by lemma, I have this. You could just inline the proof of that lemma. And if you're using it, then you could inline it again. Everywhere you can lose that lemma. Okay, in that sense, extended resolution is also doing something redundant, but it is helpful for proof length. The way this kind of reasoning is helpful for your like daily mathematical reasoning. And so I have these rules. I will make some systems out of them. And for these systems, I'm defining a derivation slightly differently, mostly because it's nicer than resolution. So my proofs are no longer sequences of clauses, but they are sequences of CNFs that I can obtain from one another. This is nice because then you don't need to consider like you have a check that is universal against all of the previous clauses. So you don't want to say, okay, proof up to this point. I just want to take previous CNF. I do the check against the previous CNF. Okay. And a derivation of a clause in this manner is a sequence of CNFs that starts with the initial CNF and derives some CNF containing the clause you want to derive, and each CNF follows by some rule. And the rules are as follows. So resolution, I've already shown you. In this formulation, basically says if these are in a formula somewhere in the sequence, then for the next formula, you could just add this.
Could be gamma plus 1.
Hmm?
Could be a gamma.
I mean, adding it to gamma I gives you gamma I plus 1. So gamma I plus 1 equals gamma I and A or B.
Okay.
And this is the resolution, the extension rule. Finally, I'm showing you concretely. You basically make these kind of the definitions that say X is the end of some literals, where P and Q are arbitrary literals, and X is a new variable. So X doesn't occur in gamma I. And you have the redundancy rule, which is like add one of the kinds of clauses that I've just shown you. And there's also this deletion rule, which Ryan kind of guessed that might be important, because so all of these conditions have some check that you need to make against all the clauses in the formula. So usually, like if you didn't have this redundancy, with just resolution, deletion would be unimportant. Like why would you forget clauses? You can just keep adding more and more stuff. Like forgetting clauses doesn't get by you anything, each place of proof set. For the systems that I mentioned, deletion becomes important. It does affect proof length because you have some check that you're performing against all the clauses in the formula. What if you're able to like remove some clauses that make some clause that you really want to derive that would be blocked, unblocked, right? So then you remove those, you derive your clause, you then continue on with your derivation. Okay, so deletion affects the power of these systems, but I won't say that much more about deletion. And this is like the notation that I have for the bunch of proof systems. Yeah, so ER is extended resolution, it's resolution plus the extension rule. BC is the block clauses proof system, it's resolution plus block clause addition. When I have a minus as a superscript, it's BC without new variables. So the new clauses that are derived cannot include any new variables. And this DBC is BC with deletion, and you could just mix and match all of those. And this is a system that I haven't defined, but just so you know, there is such a system that is like a marriage of the two definitions that I've shown. Like I've shown you SBC and I've shown you RAD. They were generalizing BC in different ways. You could just mix them together to get another proof system. And so what's known about these proof systems? And I mean, the primary interest in these proof systems, I would say, would stem from this for proof complexity. So what I mean by upper bounds here is these are some basic principles in math that you could use. What they are doesn't really matter. But like at least I can say talk about the pigeonhole principle. So the pigeonhole principle says there is no total injective function from n elements to n minus 1 elements. Okay, it's a really simple, obvious statement. But many of the proof systems that I showed you earlier have difficulty proving this. Some of them can prove it easily, and by difficulty I mean they have long proofs in the size of the encoding of the pigeonhole principle. Well, it turns out that all of these things that are hard for some systems that I've shown you, they're easy for that SPR system that I haven't defined. And it's also easy for this SBC system that I defined, but again, the definitions do not matter. I'm just telling you that if you allow yourself just a little bit of without loss of generality kind of reasoning, those actually become easy, which is hard for most proof systems. And there are also some lower bounds on proof length that are known. So this is a proof system that I haven't defined, but I will mention a little bit. So these principles are hard for these systems in the sense that they require exponentially long proofs in those systems. And what's also known is, for instance, that deletion collapses the systems. All of the systems start to simulate each other if you allow deletion. And there are no non-simulations without deletion. Okay. And here is.
Sorry, what do you mean by collapses?
Collapses in the sense that everything simulates everything else if you're given done deletion, even without new variable. So I had a bunch of systems here. Like you could imagine something like DBC minus. So this is like BC without new variable. So you have resolution, block clause addition, and the ability to just delete clause. Okay. If you took that variant for the other things that I mentioned, like I've shown you RAT, I've shown you SBC. So for all of those, if you give them deletion and take away new variables, the BC with deletion ends up simulating that. So deletion is kind of like too strong a thing that makes all of those systems actually encode. And those are like non-trivial.
Like BC minus is the weakest thing up there.
Yes.
So you're saying BVC minus
It's
is
just-
powerful if anything?
Yes.
Okay.
And I will, I have a summary of this here. Okay. Again, not everything is defined here, but just, I laid out the proof system suggestively here. Each acronym is a proof system. Minus is again without new variables. An arrow from one proof system to another says that the proof system, like here, for instance, the SBC, of course, simulates SBC because it's just a generalization. It has one more rule. Okay. And this kind of arrow means separation. For instance, I have this relationship between this system and this rat system, which says that there is some sequence of pathology, unsatisfiable formula, which is easy for this system, but hard for this system. So we know rat doesn't simulate SBC, for instance. Okay. And the stronger means that, for instance, this D-rat simulates rat, and also we know that rat doesn't simulate D-rat. So it's strictly strong. It generalizes it and is also not simulated by it. And I've laid out these in this manner, because this is meant to have like 3 axes. So BC is at the origin, it's the simplest notion of redundancy. And if you go in this direction, I haven't defined it, and I will not define this. You give the proof system some kind of deletion, a little bit of restricted form of deletion. You say maybe you can delete those clauses, but not all clauses. And in this axis, so in BC, we're looking at a literal in the clause to justify its redundancy. So in this axis, you're saying, okay, I will look at multiple literal in the formula. And in this axis, you're relaxing the implication relationship. So you were saying tautological, you were saying with rat, you would be saying tautological over subsume. Okay. And since those are independent, you could combine them, like I said. So for instance, SPI is like a marriage of these two systems. And the black arrows are already done. So the red relationships are what we so we prove a bunch of separations across the weakest generalizations of BC along each axis. Okay, and it's nearly complete if we could resolve, like whether there might be something here. Like we don't know exactly the relationship between SBC and GR and SBC and rat, and resolving that would say, if you have like qualitative, basically the punchline would be, if you have qualitatively different rules, they turn out to be quantitatively different, unless you have this deletion thing.
What does S stand for again?
Set.
And that refers to what?
Set block clauses. So you consider a set of clauses, set of literals.
So just to make sure I understand it correctly, when you just say deletion, which things are you left to leave? Any arbitrary clause that have to be redundant or some other?
Doesn't matter what it is. You have the CNF, and as a proof step, you can say, I now move to a subset of the CNF. I just forgot about those clauses.
So it's no longer equisatisfiable, but that's okay.
For refutations, it's okay to use those, right? Because if you've deleted something, you could only turn something that was unsatisfiable, satisfiable, right? So if you're doing that and still getting to a contradiction, then it's sound. For deriving things from satisfiable CNFs, it's not perfectly sound. Okay. So there it requires some extra conditions to use. But we are just talking about refutations of unsatisfiable CNFs. So you might as well just go ahead and delete everything you want, as long as you give me a valid proof at the end.
Right. But the remark about equisatisfiable didn't apply to that. It applies to adding new things.
Yes.
Yeah.
I mean, because I didn't need it for that definition, I didn't define it that way, but equisatisfiable actually says that so redundancy actually is defined in the literature as saying removing or adding that clause from the formula preserves satisfiable. Okay. So how do we prove those? I mean, the appeal of those is I will give you almost like a recipe for proving those by using previous results as black box, which is quite nice because often in proof complexity, when you're trying to prove some separation, those are kind of accidental. You have like some principle, which is easy for some proof system. And you say, well, is this easy for the other system? You try to prove a lower bound, and then, oh, it turns out to be hard. You're lucky you got a separation. So they're not like super directed. There are some approaches that are more systematic, and they are similar to what we are doing here as well. In very short, what I will do is I will take formula that separates external resolution from those crude systems. I will do some manipulation to those formulas such that the resulting formula will be easy for one of the systems, hard for the other system. And I will be able to, like, the proofs should be simple while doing this. Like, I don't want to work too hard to prove a lower bound is the idea here. That's why I'm calling it almost like a recipe. And when doing so, the way that the formula that separates the external resolution from the system that you're trying to prove a lower bound against should not matter. Okay. In the other approaches, generally that also matters. Like, you have to have some extra conditions on, like, the shape of the proof that you have to be able to, lift the results. And this simulations that I have depend on a peculiar property of these systems that we have, which is called an effective simulation. This is not really a simulation, it's an effective simulation. And I'll explain it by an example of this level. So suppose I give you some formula that has an external resolution proof of some length. Okay, you can add to it the new variables that you would use in the external resolution proof to get some formula, which then BC without new variables has short proofs of. This seems like a technicality, right? So I just put the new variables into the formula so that now I can say, oh, my proof system is BC without new variables, not BC. Okay, does this make sense? Yeah.
No, I'm a little bit confused. Like,
so you have your formula and you have two clauses that have variables that are not occurring in the formula. You just tack them onto the formula. Now, relative to this formula, if you make an inference that involves X, the result is not technically a new variable. Like, you could be deriving a clause from this variable, a clause from this formula that contains a new variable, right? And that variable would actually not be new because it's already in X.
Yeah. What is BC again?
BC is this block clause proof system without new variable.
The role of X here essentially applying or supplying the variable.
Yes, you're basically incorporating the new variables into the formula. Okay, and the new formula has a short proof in BC if the original formula has a short proof in external resolution. So you're like kind of in a hacky way, you're simulating external resolution technically without using new variables. But you actually are, but technically, like with respect to this formula, the variables are not new. They're already included within the formula. So if you know how many variables to include, then you could just say, well, you give me an external resolution proof of some formula, let's say pigeonhole principle. To the pigeonhole principle, I have two clauses that contain these clauses, like these two clauses with the new variables. And then I do something which allows me to simulate the external resolution proof. So I suddenly, regardless of whether gamma itself is easy for this BC minus or not, the resulting formula with the new variables is easy for BC minus. And everything is without new variables, technically, because you've just built them into the formula now. Okay. And I was going to show you like the sketch of how to do this.
So is that the same n there? So the size n and the number of variables, x1 for xn?
Yes, m is actually too much. You don't need to make it m. You just need to say how many new variables does this ER proof use, and you set m to be that. I want an extra variable in the slide. Okay, right? So you just say I made 10 definitions in this ER proof. You just need 10 variables. Even though if the ER proof is actually longer than 10. Okay. And maybe actually I can show you why this is the case. So you basically need to, you both systems have access to the resolution rule. You basically just need to simulate the addition of this definition clauses. Okay, in block clause, in this BC minus, what you do is you add this clause. This is blocked for not xi. Why? Because the only clause that xi would occur is here, and you have not y here. Okay, and this is blocked in the same manner, and this is blocked because you only need to check against these clauses. But here you have P and Q, here you have negations of P and Q. So you add these in sequence as block clauses, these actually represent this. So then this Y is extra here, but that's why the unit clause is included. So you just resolve those two against that Y, and you basically have done the same thing in this BC, technically without using new variables, that we are. Okay.
Maybe the reason it's clearly is just mere technicality. Okay. And so we will just, if we push this idea further to get separations. So suppose I have some formula that's easy for ER. Again, like remember this packing on new variables thing makes it easy for this BC minus system as well. And to separate two systems, I will just incorporate these new variables, not using these two clauses, but using like gadgets, such that it's useful to one of the systems, but it's not useful at all to the other system. So with the tacked on new variables, the resulting thing will be as hard as gamma is for one of the systems. It will be as easy as the formula is easy for ER with the new variables. Okay. This is basically what I said. Yeah. And by that, I will achieve this by like guarding the variables. I won't get too much into it, just want to explain it with an example. Like, since you have this universally quantified condition that needs to be satisfied against all the clauses, and since you don't allow deletion in those systems, you just tack on like evil clauses that allow you to impose some conditions upon the clauses that can be blocked. For instance, take this formula. We know just by looking at this, even if like you have some larger formula next to it, any clause blocked for X with respect to any formula that includes this has to include both not Y and Y, and it's topological and so useless to derive. So for instance, you know that if you have these two clauses appearing, then it's useless to try to derive anything that's blocked for X. This is like the vague, simple version of the idea that will derive all the examples. And I will not give you proofs, but I will show you the constructions that separate the pairs of systems that we have. So
the question.
Yes.
So like the way you're going to show that like Q is unable to achieve any speed up using included variables, is this going to like come from like some known lower bound against Q, or it's going to come for like some easier reason based on how you're going to set up the guards?
It's going to come from some lower bound against Q, plus I will show that that lower bound translates to the version of the formula with the new variables already there. Okay. And then the upper bound will come from just showing that one of the systems doesn't care about these guarding clauses. It can just go ahead and simulate the ER proof somehow. Okay. So for instance, this kind of construction separates RAT from these two systems. And let me explain what this is. So you take the original formula, which is unsatisfiable and should be hard for both of these systems. And to each clause in the formula, you attach this new variable xi. And again, to each variable in the formula, you attach this new variable not xi. Somehow, this makes the result, this f gamma, easy for RAT, regardless of whether gamma is. Because as long as it's easy for X-time resolution, RAT just goes through and simulates the proof. But this is at least as hard as gamma is, in the sense that you did this, there are new variables in the formula, but these are just completely useless for GER and SPC. And the non-trivial part of this is proving that it's indeed hard for the two proof systems. And we can basically, like, in a rather systematic manner, construct those gadgets. I'm not talking about it, but there's a method to the way you construct those gadgets. Like, I'm not pulling those out of a hat. But yeah, I will not get into that. So to separate, for instance, RAT and the other systems in the other direction, you have this gadget. You have this time two new variables that just says xi if and only if yi. Okay? Somehow, the two systems, for different reasons, are able to still simulate the ER proof, but RAT is unable to do anything meaningful with these new variables. Okay. And then as the system that you're probing the lower bound against gets more complicated, so do the gadgets. This is a bit of a more complicated gadget, which has a parameter in it. This time I'm adding 3 new variables, and the gadgets from the previous constructions actually make an appearance here. And this turns out to be easy for GER. GER is just a little bit of deletion, so I haven't formally defined it. But then you can choose S in this formula in such a way that the resulting formula with the gadget applied turns out to be as hard as gamma for SPC. Okay. This is more complicated than the other ones because SPC is a more interesting proof system compared to the others. Okay. And I had a proof sketch that I condensed down, like the simplest lower bound proof that I condensed down to a slide, but I will just skip it. And so for the results, like what's the take home? So I have a recipe for proving separations in quite a modular way where you can just take known results, even upper bounds and lower bounds, as black boxes and reduce the act of separating two systems to just mere syntactic manipulations, followed by not too hard lower bound proofs. And this also gives like an almost complete picture of the weakest generalizations of BC. Like I mentioned, we don't have the separations from SBC unconditionally. That's why I had these asterisks here, because there is no unconditional lower bound known against SBC. So these are saying basically that unless SBC minus simulates ER, it doesn't simulate this system. Okay, so the results about SBC are conditional right now. Okay, and so what more to do? The most pressing question is what is hard for this SBC or this its stronger variant, which has upper bounds against every hard known thing. And also, this is a little bit unsatisfying that you're doing separations in this way because the formulas are not really corresponding to anything natural. Like I cannot summarize what that gadget H did, for instance, does, for instance. So it would be nice if we could have natural principles, like for instance, the Fujinol principle separates resolution and cutting planes. So people are using metaphors like resolution cannot count, cutting planes can count. So we cannot say metaphors like this for these systems. And also the study of these systems right now is basically living on its own island, as like separated from the rest of proof complexity because relationships between these systems and the rest are not known, or at least not much is known. So that would be an interesting thing to resolve, like to connect it. And actually the most interesting person here would be, like, is there a new subsystem like of Brega that's like above resolution, strictly stronger than resolution that DBC actually simulates? Like if you have deletion and it's block clause without new variables, can you simulate having access to richer syntax? Right. And also like this is kind of a generic recipe, so it would be nice to find other uses of the same idea in proof complexity for separation. And that's it. Yes.
Can you go back to the picture with the cube? Yeah. So first off, like so you have these like open. If I'm okay, I might be understanding something wrong and saying something silly, but how I understand, I think the open questions are like whether there's like red dots in the other end of the dashed lines, like
so the open questions are whether this will solidify and turn into an arrow. So the convention that I try to follow is the arrowhead, even if it's like an arrowhead or a
I see.
is a weaker head.
Okay. Yeah.
So this arrow, so you could first come up with a simulation of GER by SPC. This arrow would then be solid and like this, you know, it would be strictly stronger. But I'm saying unconditionally we know that this will not happen. Unconditionally we know there's a option.
So which one do you think is the answer, that this becomes an arrow or that this becomes a?
The answer I think is the symmetric one, like all of the weakest generalizations along different axes are equal.
Both ways separation. Does that also imply, so this like bottom line, does that also imply that that becomes a stronger arrow because there has to be a separation between that and DBC, or am I reading it?
Yes, because in that case, so you can take these arrows, you know, this simulates this simulates this. Okay, so if something has a short proof here but requires a long proof here, it has a short proof here but requires a long proof here, so this also becomes like this.
Okay, and so that's what you think is the truth. Yeah. That these are strong. There's a big separation between this triangle and the rest.
Yeah. And also, like, I'm not showing, but this cube actually extends upward and out of the screen. Like there are further generalizations.
Yeah, we can make up new.
You can keep making up things, but this SPC is where things start to get interesting, and SPR is things where where things start to get really interesting, and these are probably like stupidly strong.
Okay. Thank you.
I just have a complaint that's not for you, because it's not your fault, but proofs and reputations are the exact opposite of each other.
Yes.
And you're using them the same way. I mean, not you, but the field uses them
At
the same
the
way.
meta level, you do you translate like the negation to the other side.
Yeah, nevertheless.
Okay, yeah.
Reminded one time we had a Bob Harper over for some dinner, and he said, I have a headache, get some aspirin. And the answer was, you don't have aspirin, but you have some non-aspirin. So, oh, that's fine. So,
Yeah. I mean, the way people generally actually say when they're trying to be perfectly correct is proof of unsatisfiability or refutation of satisfiability. So I say proof and refutation, but I omit the like the other part of the other noun that should be there. And also, like, reputations are as good as proofs for those purposes. Like you could just without agenda always talk about refutation.
Okay.
I'm just saying proof because they are called proofs.
Yeah, I'm gonna have a hard time explaining this to my students
Okay.
in the spring when I teach the constructive logic class, because proofs and reputations are
Yeah.
very, very different things.
Okay.